Welcome, first of all, also to our remote audience. You're here for the talk Scaling to Human Level Visual Understanding with Self-Supervised Learning. You may have noticed at this conference, but also I think generally maybe in your lives, that AI and robotics is nowadays really everywhere, right? It's of course researched heavily. I think we had like Boston Dynamics here today, but it's also put into practical use. So we have some exhibits, right? People put them into their factory floors. But what we see is the training kind of reached its limits, right? We don't have enough labeled data. What does that mean, right? You have data that is kind of annotated. What does it mean? What do you see here? What do you need to do? We even saw this morning, maybe some of you attended the talk, people use video games, right, to train their robots, Counter-Strike or something, right? But of course, how does this transfer to the real world? Maybe that's not really scalable. So the question is how to scale, right, without needing synthetic or virtual data that doesn't map. And Yuki is going to talk about self-supervised learning using videos today. I won't take too much from his talk, but just briefly, learning from motion, change continuity in the videos. I think it's going to be very interesting. But let's talk about our speaker real quick. So Professor Dr. Yuki Asano is here with us. He's a full professor at the University of Technology Nuremberg, where he leads the Fundamental AI Lab. He works on cutting-edge AI research in computer vision, multimodal learning, and large language models. He was previously assistant professor at the UVA, University of Amsterdam, one of the big ones as well, and got his doctorate in philosophy from the University of Oxford. Now, at TNG, we have people from various backgrounds, physics, maths, computer science, and I read your CV, and I had to laugh a little bit because you do have a bachelor in physics, a master in the area of maths, and you do a PhD, or you did a PhD which is like computer science related, right, in your professorship as well. So you're kind of the perfect speaker for this audience, I want to say. So please give him a very warm welcome. Now, before you start, real quick, organizationally, you guys know the drill, questions after the talk, right? We will have remote and local questions. Remotely, please ask via Zoom. They will be spoken out loud. And please use the microphones for questions. Thank you.
All right, cool. Yeah, thanks everyone for attending. Thanks for the invite. I used to be a participant here, so now I'm very happy to be also giving a talk. I was also already introduced, which is great. Our lab does research on a couple of things. So the University of Technology Nuremberg, first of all, for those who haven't heard, was founded 5 years ago, first state-founded university in Bavaria since 20 years. Also called the AI University, so we're really focused on this topic, around 25 professors right now. As you already mentioned, I've been to a couple of places before that, also work as a freelance ML consultant, and the focus of today will be the self-supervised learning part. We also do a bunch of stuff on multimodal learning. I know some of you might have heard about the model ChatGPT, which can understand images, right? We also do analyses on these models, which still have a lot of failure cases, but I want to convince you of something else today. All right, so also I lost my glasses, so now I look like this. Our lab does these research topics, as I just mentioned, and a big part of it is really this left-hand corner, video and temporal learning. Videos is the thing I'm going to try to convince you today to think about a bit more and talk about it during the next coffee breaks and so on. But before that, I want to mention a bit about the current trend of so-called foundation models. So foundation models, I would say, I mean, you can group them however you want, but I would say we have 3 types of foundation models at the moment. One big type is these multimodal LLMs. These would be ChatGPT, Claude Sonnet, etc. They are now helping with writing, coding. Of course, for assistive technologies, they're great because they understand images and videos, right? These generative models, text conditional ones, you can type something in, generate a video, generate images. And then these general image understanding models. These are basically, I would like to equate them a bit more to like the human eye in an ideal scenario. It perceives the world, and ideally it can adapt to new topics or new things it sees very quickly. Like if you're an adult and then you try to become, let's say, a doctor, you learn to understand X-ray images, and you don't need to see millions or trillions of X-ray images in order to work really well in your domain. And so if you have a model that is really good at general understanding of visual data, that's a foundation model. And that's more or less the type we're going to be talking about today. In terms of foundation models, this term has become, of course, very popular nowadays. And just, again, my personal take is there's three things which made this possible. So we have a very flexible architecture, the so-called transformer architecture, and we have found ways that these models train, which is quite predictable, which means companies can actually invest in this and know what they're getting, which is very nice. You don't have to do guesswork. You know if you put this much in, you will get this much out. And of course, we have now much more data. And a large chunk, or the majority of it, is really unsupervised. And we'll get to this point about what unsupervised versus supervised means in a bit. And then some considerations about the foundation models that we're also excited about is taken from a paper from 2 years ago. The current speed of progress in terms of the data used for these LLMs is growing like crazy. And actually, we're likely going to run out pretty soon in terms of text data, right? Right now, we're generating new and synthetic text data using reinforcement learning. That helps, but is, of course, extremely expensive compared to the free data source you have on the internet. Another consideration, and these are sort of topics that you hopefully talk about in the coffee breaks, is also creativity. I mean, Ada Lovelace already said it in 18-something, that we'll have algorithms that can be creative and that can make music, poetry, and now prove whole mathematics conjectures, which hasn't been proven. This was just 1 or 2 days ago. This is going to get talked more and more about. And lastly, this point about compute scale. Let's see if this works. So here's just a visual illustration of what this thing that we call scale means, right? So up, one back. Our back is here, all right. So one more time. You can see that at like a 1x level of compute, you can barely see anything, but you apply 32 times more compute. So instead of one server, you have 32, or instead of 1,000 servers, you have 3,200, 3,200, whatever. You suddenly get realistic things. And I think this is quite visual, what this means in terms of scale, what scale means. These scaling laws, these plots, which just have double exponentials, they're not very graspable, I think. And now this topic of self-supervised learning, which is what I want you to take home today, basically. You all learn in kindergarten supervised learning, right? So you have images, and then you have labels. For example, this image is called railroad crossing, and this bird is called trogon, and so on. And obviously, sometimes this is pretty easy, like railroad crossing. But for things like bird names, cat names, dog names, you already need some expert knowledge, right? Like trogon. I wouldn't have known this. Moreover, if you want to have something that's pixel accurate, it takes quite a while. It can take up to like 60 minutes to make a really fine map of what is what in an image. And the same goes for text, like you can summarize these and you can find bugs and so on. And all of this is typically used in supervised learning. So you have data and you have outputs, and your model mimics a human, basically. The model gets some input and needs to predict the output. And this has been working extremely well with deep learning. We can now learn really complex relationships like image in, all kinds of object categories out, and so on. Now, this right-hand side is the expensive part, right? And so self-supervised learning now tries to generate something from the raw data itself, namely the self-supervised learning signal. So that means we're going to try to learn something from the data. So it's kind of like you go to school, but there's no teacher, and you still try to learn something. And that's entirely possible. And so the easiest example in this case is language. So for example, if you have a sentence like, oh my God, the volcano is and then what the LLM needs to do is predict like what the next word is. So in this case, erupted. It needs to say that the probability of the word erupted is high, and the probability for a word like erudite is low, because it just doesn't make too much sense. And that's all the LLM is doing. And you can see that, this is basically the task with which we train this large language model, which is very simple. And now the reason why this is self-supervised is you find this data all over, right? It's pure text, and no human has like explicitly said this sentence is about this topic or whatever. You just find the data. Yes, the data is human generated, but there's no labels attached to it. So that means if you don't have humans that manually label stuff, you can scale it extremely well. You just find stuff on the internet, you train on it. And a similar case is happening for images. In the case for images, a very simple, explicit analogy here is you take an image and you remove a couple of parts from the image, right? You do some masking. And then you push it through a model, and then the model needs to predict, oh, what was actually masked here? And if it sees these parts of the image, oh, it needs to predict it's a flamingo, and because it knows where the locations are, it needs to predict all the remaining patches. Sort of makes sense. One would think this is the ultimate equivalent for images in terms of the success of large language modeling. But if you think about it, there's some really important differences. Images don't really have these natural units, right? Words or like tokens, they have individual meanings. We have some relatively soft, but we have some rules of how they get combined. We don't, in images, have a fixed vocabulary. If you think about these grids, they are like, for example, 16 pixels by 16 pixels, and of course red, green, blue, so that's 3 numbers. There's a huge combinatorial explosion of all the possible patches that you could have. While with words, we typically get by with 200,000 tokens or something, which is comparatively little. So all of this, and of course, like being able to generate an image doesn't really mean that you understand the image, right? You can draw all kinds of things, but you don't really understand why this is the case, or like what's happening in the foreground, etc. And so all of this has led to quite a diverse set of self-supervision methods in computer vision. And that's why I do research, basically, because for computer vision, things haven't been solved. For the language game, we know what kind of laws work well, and we talk about modifying the data with RL or with human feedback, etc. But for computer vision, we're really at this basic stage of trying to figure out which algorithms do even scale. And now, the key aspect is the part about self-supervised learning from videos. And so first of all, warning to not give this slide to your babies, which is, this is ImageNet visualized. ImageNet is one of the most common computer vision data sets, arguably the one which ushered in the era of deep learning. And this is 1 million images. If you flicker through this for, I think 24 hours, 12 hours, you get to like 1.3 million images. And this is how current visual foundation models are basically trained, right? These models see a bunch of images, essentially flickering. I mean, they don't have a sense of time. But I don't know how to stop this, but don't look at this, you'll get crazy. But actually, if you give this to primates, and researchers, some crazy researchers have done this, given this sort of flickering images to monkeys, that deteriorates their sense of vision. Because they don't have any visual continuity, right? And I don't blame them, I would also go crazy. But in fact, like, they can not track objects after this anymore. And so we want our vision models to be able to be pretty good. And so I would argue that the next family, and actually this is already happening, the next family of vision foundation models will be trained by videos. One reason is we will have something like visual development for AI that's a bit closer to how current infants and toddlers learn vision. Secondly, only with videos can we hope to really learn something about physics. So if I gave you just a single frame here, you wouldn't know what's happening. Even with the video, you don't know what's happening, but at least you know physics people roll down, right? And this is actually a festival in the UK where they roll down a piece of cheese and you need to capture it as quickly as you can, and always broken arms and so on. But the point is clear, right? With just still images, there's only so much you can learn. With videos, there's a bunch more, and especially physics, especially moving around things, friction, all of these things. Similarly, if you ever hope to have a robot which works at home, cooks for you, cleans the kitchen, it shouldn't be that it does something, takes a picture, computes it, and keeps doing something. It should probably have a very good understanding of video as it comes along. And lastly, this point about insane scale. All of these platforms, from Netflix to TikTok, they're video-based, and I have this anonymous source here. Oh, can you turn down the lights, please? Does this work? Oh yeah. Well, it's good enough. It's a shady guy that I talked to. Well, hopefully not too shady, but told me. So he works for the state monitoring the internet traffic, and actually 90% of it is video content of the internet traffic. And I mean, you can find this information otherwise as well. But still, this means actually, like, working on video makes sense, right? So if we know something from deep learning is that the more data you have, the better it is. Yet, like, we're not tapping the 90% of the data source on the internet, right? All the other stuff, like text or images, they're tiny compared to what we could access in terms of video. So yeah, there's this point about scalability, just mentioned it. There's also this middle thing called weak supervision, which is typically data where you have images and people have added some sort of annotation. For example, these would be hashtags in Instagram, where people sometimes use something sensible like my Labrador retriever, and that could be quite a useful label, right? If that dog is indeed in the image, but if it's just hashtag feeling cute, then it doesn't help you all that much with learning, probably. And still, that's tiny compared to all the raw footage. Like, every Tesla that's driving around collects terabytes of data every day. All the satellites collect petabytes every day. The surveillance cameras, and I think you get where I'm going, right? Like, the raw data is just insane. And most of it you could use with self-supervised learning. Also, if you're trying to get these generic vision models by supervised learning, you will struggle, because if you rely on labeling and you're trying to do car detection, which would be quite relevant here, right, in this motor world, you would have to constantly relabel. Moreover, like, it's not just cars, it's mobile phones, it's clothes, it's all kinds of things. You have to constantly pay for it just to keep up, and you never know when to keep up either. Except when you're, like, trying to detect Lada cars, then you're pretty lucky. But this is almost never the case, right? Like, everything is changing, so relying on labeling just is not the most cheap way, actually, to do things. I have to say, though, that you need labeling at the end, right? So if you want to detect whether something is cancerous or not, or whether this piece of metal is broken or not, you need some sort of labels, but you shouldn't rely on it for this general training of the neural network, or pre-training. Lastly, if you're trying to get a good neural network that perceives the world, maybe you don't want it to be biased based on language. So if you type in house into Google image search, you get all of these kinds of images, right? And they're all houses, but they're all different. And the current training of CLIP, SIGLIP, etc., which is sort of the prevailing paradigm of how people train image models when they have text available, is basically trying to put all of these into a single vector that's identical if they have the same caption. And that's kind of, like, sad, because then you get all the differences get turned away. And of course, you have some sort of bias that comes from the language as well. And if we're just trying to learn a basic eye like that of an infant, essentially, that's insanely flexible and robust to all kinds of occlusions and things like that, probably we want to try it without language. At least that's a scientific motivation for me. Similarly, it's interesting to see how far can data alone go. If you have labels, of course, you can make things work, but then it struggles often with generalization. But if you just have data, now that's quite an interesting challenge. All right, so that's sort of the overall motivation. I'm going to show you one of our recent papers that we presented at one of the top conferences in our field, called Time Does Tell, Self-Supervised Time Tuning of Dense Image Representations. And this gives you a bit of an overview of this field of self-supervised learning already. So often in the domain of self-supervised learning, as I said, in images, for example, we learn models the following way. So we have, for example, a model and we have an image, and we modify this image, for example, twice. Here, we rotate it, maybe apply a slightly different zoom in, cropping operation, and then we say, oh, the thing that comes out, that needs to be similar, these two vectors, because this is a cat and this is still a cat, right? And so the key principle that we typically apply here is called view invariance. And views can be induced by so-called augmentations, for example. And this might be okay for like a video like this, right? Where, for example, if you apply this to if you think the first view is the first frame, and you compare this to the last frame, yeah, it's still a car in the street. I mean, the car is now in the sun, but that's basically the same content, right? It's fine. But does this generally make sense? For example, if you have a video like this, where the frame is that, and then the last frame is pretty different. I mean, I don't know if they have these types of cars here, but it probably wouldn't make sense to say like, oh, model, look at this image, model, look at that image, and then we're going to train you to say these two are the same. It's almost as much of a crime as saying like all of the houses are the same, right? So forcing individual frames to be invariant is extremely limiting, but people have done this for a long time, actually. And the solution is quite obvious. Instead of saying on an image level, one vector per frame, basically, that these two are the same, we should apply a dense matching, a dense loss. So basically, we can try to figure out where's the numbers played in frame 1, where's the numbers played in frame n, and then say, okay, the number played hasn't changed, right? Now the surrounding areas might have changed, and therefore the way the neural network sees this number plate might be slightly different, but the number plate itself is still the same. So these two should be the same. In this case, the vectors associated with these image patches should be the same. And the same goes for this bush in the background, for example, and so on. Now, the key thing is, like, how do we find these green and turquoise boxes, right? We're in the self-supervised regime. We don't want to rely on, like, a human drawing boxes around every frame. That's not scalable. But we also don't want to rely on another model telling us, okay, these two things are the same, because, well, then we would have known this already. So the key thing we do here is we do this in a self-supervised way. And I'll tell you just a high-level intuition of how this gets done here. So at the top, we have the video, frame 1 till frame n, right? And then we have the neural network psi. We have the neural network here drawn twice, so it gets the one frame, and it also goes into the last frame also goes into the model. And then what we do is we do clustering on the first frame, and the clustering is happening on the pixel level. So every pixel gets associated to a cluster. You can think of it kind of as grouping the pixels into, let's say, horse category pixels and background category pixels, for example, in a very simplified way. And then what we do is we take these assignments and we warp them with a model which we call feature forwarder into the future, right? And so this can take a look at the video, how it evolves, and says, okay, based on how the video looks, these features should end up at these locations. And of course, we have the final frame, so we can actually do the comparison quite well. And so we can actually compare, oh, if we actually just plug in the last frame, how does it look? And then we can compare, and this is our loss, our time tuning loss. It's very high level, I know. For those of you, and I might put the slides somewhere online, I added like a nice Google image, GPT image generated figure on optimal transport-based clustering, which is sort of the mathematical intuition behind it. It's just a way how you can cluster that's regularized, that's extremely fast and differentiable. So you can ask me about that later on. In terms of high-level intuition, what we did is here shown all the way on the right-hand side. Previous methods, as I've said, tried to use individual frames as augmentations. So they pretended, like, for example, frame 1 is the same as frame n, or they trained video models, so that's in the middle, so that's great. You need models that take in whole videos. But what we tried to do here is we tried to have image-based models, so these models get individual frames, but the way we train them is with a temporal loss. So we take into account the whole video, but the model itself is a basic image understanding model. And the result is the following, that like, if you assume nothing happens on the video, so you ignore time evolution completely, it doesn't work. It has some baseline performance, which is not 0 because we start off with a pre-trained model. But if you actually apply time tuning, you get a big boost, and the same goes for like using multiple frames. So indeed, we're actually learning something from time. And I'll spare you the other tables, but we're state of the art on these results, which is nice. A qualitative result here, you can show that we can, again, do this grouping, this clustering of pixels, And you can see that in our case, oops, I'll leave this better on. In our case, we get much crisper boundaries, while the other methods, either they overclassify or they don't work nearly as well. And this is completely without supervision. So the model has never been told camels look like this or background looks like that. It has just been trained on pure data alone, and it gets these really consistent maps, which is nice. Some more results. Yeah, and of course, like in theory, afterwards, a human could come by and say, oh, all of these blue clusters, I know this thing that's called a car, and then you can, of course, propagate this label, and you can be quite efficient in terms of labeling afterwards as well. All right, so from this paper, a few key takeaways would be that videos provide good signals. Don't use frame-wise invariance. That would be exactly ignoring what's cool about videos. And in this paper, we improved upon like a sort of state-of-the-art model back then, which is called Dino, and we got a bunch of improvements. And for scientific sake, like there's been a bunch of research on this in the past, right? As I said, but they mostly considered these two frames to be equivalent, etc. And since 2020 onwards, there's been a bunch of researchers, including us, working more on these video-based pre-training. And also this guy, I don't know, some people might recognize him. He's a Turing Award winner, Jan LeCun. He's also working heavily on this and also just founded his own startup, basically working on this, where he tries to learn using video data alone. He calls it world modeling. It's essentially like a fancy way of learning from video data. And yeah, this is getting quite big, and he's pretty successful at this. So, and yeah, also we've been keeping up to date with this as well. So since this paper, which has been a bit outdated now, we did a few upgrades, for example, at ICCV and ICML recently. And the key idea was we improved this clustering and the tracking. So for example, I talked about this number plate. This was based on a single patch. Now we can do this much more precisely on point tracks, for example. All right, and yeah, it works better. And we have a bunch of more post-training work. So what I mean with post-training, and this is sort of a common term in the LLM domain, but not so common in the computer vision domain. What this just means is we take a pre-trained model, for example, from Meta, for example, from OpenAI, and we try to improve it further. And this typically can be done very cheaply, with very little compute, but with a smart loss. For example, with a loss that uses a video. And that's what we do, and typically this works pretty well. And here's a bunch of other works from our lab where we recently tried to do this. Yeah. Also, is there someone working in the medical field here? I'm curious. No? Maybe? Okay. Another aspect that's quite interesting is, for example, if you want to learn from video and images together, and this paper I'll keep very short here. You can see that, like on the top row, that's how a normal adult heart would be beating. So this is a video sequence, and the abnormal one is in the bottom. And I'm not sure if you can spot the difference. I sure couldn't, but that's the task we're trying to differentiate here. So we really need very fine-grained video representations in order to be able to do this. And also, like you can see, for example, in terms of if you compare it to a normal video of someone preparing some cakes versus these heart-based videos, all of it is just light up. So that just means all the frames are very similar to each other compared to natural videos where you have a scene change or perspective change. So this makes it quite difficult in general. And so the only thing that we did here is apply a very similar setup of also clustering trajectories or clustering the dense features in the image space, but we at the same time also learn a video model. So we learn both video model and image model, and they cross-supervise each other. And this worked quite well, and which makes sense. Like the video model then picks up more on the features which really, really require time, and the image model picks up on all the details that, well, you can see just from the images alone. All right. And now, sort of, this is a pretty funny work, I think. So we almost won Best Paper Award at ICLEI with this one. We were, one of the nominees. And so we just, in the previous paper, we explored that time works pretty well, right, in pre-training. But we didn't really consider this perfectly because we still we were in the post-training setup where we started off with a model. So now here we wanted to study the extreme case. So try to learn from a single video from scratch. So basically have a baby born and it can only see a single video and see how well it can develop vision. Because as humans, we don't get millions of videos, we don't get thousands of videos, we basically learn from a single video, which is our eyes, right? Interrupted by some sleeps, but it's essentially one continuous stream. All right, so then we had this goal, and now the goal was how to pick a video. So obviously, okay, we want to have one video, so let's pick a very long one. But it should have a bunch of content, right? Ideally pandas, dogs, planes, everything. And then, okay, and also it should be high resolution. But that already sounds like data curation. And as I said, like we want to be self-supervised learning, no data curation, it should be scalable. And then actually, this is pretty much the solution, get out, have a walk, walking tours. So I don't know whether you've seen them, but YouTube is full of them. People just attach a high-res camera like a GoPro or like DSLRs on their chest, and they walk across cities. And you have hour-long footages online that roughly look like this. They're very relaxing to watch. So we collected 10 videos. They're all 4K, and open source them. This is very easy. And the cool thing about this data set, especially if you compare it to, for example, the ImageNet data set, which I showed to you, you can fully watch it. You can make sure there's no naked things in there, right? Well, with the image-based data sets, you cannot. And that's why like people still, to this day, keep finding not safe for work or illegal things in these image-based data sets, because it's just not scalable to look at it, to look at every image, and automated models always have failure cases. And here, you just put it on in the background, you can look at it, yeah, it's very relaxing to watch your whole data set in a few hours. Alongside this new data set, we also propose a new learning method. And the new learning method has one key component, which is called, where we again use clustering, which has a multi-object tracker. So here, just to give you the high-level ideas, so the vision transformer has so-called heads, and they all spread attention across different places in the image. So spatial patch features, so for example, number 1 could be in the top left corner, and N could be in the bottom right corner. So all of these are locations in the image. And typically, these models tend to look at the same area. Let's say in the middle, because most of the interesting things that are happening are in the middle. And this is pretty problematic, because in these videos, there's a lot of things happening. If you always just look at the middle, that's pretty boring. So in this case, we do, again, optimal transport clustering, which gives us some sort of regularization that forces these heads to spread their attention. So basically, this model has typically 6 types of heads, which can look at different places, and we are softly enforcing that these heads look at different locations. And whether this is working, and this like a bit of technical thing, but we can visualize this quite easily now. So for example, we give each head one color. So we're just going to take a look at 3 heads and give the first head the color red, the second head the color green, and third head the color blue. And so this is a video sequence. Column 1 is frame 1, column 2 is frame 2, and so on. And in the basic case, we can see, okay, so one of the heads is looking at the car, so therefore the car is blue. That works fine. But you also see, for example, the scooter being turquoise. And turquoise, of course, is not one of the RGB colors, but instead is a mixture of green and blue. So 2 heads of the transformer are looking at this, which is not ideal, because now like they're mixing features for this particular object. Instead, if we apply what we propose with sync on Knop, you can see that now all of these maps are red, green, and blue. So there's no mixtures happening, which is extremely nice. Because what this means is actually we have this ability that multi-object tracking just emerges. So as I just showed you here, right? Like there's nowhere where I said like, okay, let's label individual objects and let's follow these objects, right? I didn't say anything about that. I only said apply this thing, which is just some regularization, doesn't require labels essentially. And then as a result, we get these things. So for example, in the top video, it can kind of track these individual objects. This just emerges naturally from this type of training that we do. Same for the bottom one. It tracks sort of the cyclist and this pedestrian quite nicely. And this kind of a ability that if you have a self-supervised loss that sort of makes sense, it also learns pretty reliable things. And yeah, we get good representations. I'm going to skip that one. Yeah, and so conclusion from this one is, yeah, walking tour videos are really great. They're continuous, which is extremely useful for learning, because whenever, for example, you have movies, you have close-ups, and you have a different angle, then you have an explosion, then you're in a different location. That's also not easy to learn from, right? Like imagine, again, you're some sort of baby, and you're seeing this, and you're trying to make sense of that. It's very, very difficult. Therefore, if you want to learn models, these types of data is really, really useful. And now, for the last paper, I have to rescind one of the messages I had earlier, right? Like, we always have lots of raw data. And I don't know who might have thought about this, but there could be someone saying, like, oh, but what about 3D? Like, like 3D, like the best data set, the best paper, just uses like 139K scenes, which is tiny. And actually, most of them are simulated, right? 120K of them are simulated. So actually just like 20K scenes are real LiDAR scans, or 15K. And this is tiny, right? It's not in the millions, it's not in the billions. So 3D learning has been severely limited by the lack of data, actually. So how do we scale 3D without 3D scans? And this is the question we address in the paper, 3D scans, scalable pre-training from video-generated point clouds, which we're gonna present in 2 weeks in Denver at CVPR. And what we do is actually pretty simple, and it's all in the name of how can we scale learning. We take web-based videos, which again, we just download from YouTube, and then we apply so-called geometry models, which can give us a rough estimate of how the 3D geometry looks like, which have been increasingly getting better and better. And then you get a sort of noisy video-generated point cloud, and then we develop a new learning method which can deal with this noisy data, and that's it. And the thing is that we start from something that's extremely scalable, and in the middle we only have these geometry models, which once trained, you can apply them as often as you want, right? This works pretty well. So let's take a look at the video-generated point clouds. It roughly looks like this. We have these tours, so basically you can type in a real estate tour on YouTube, and then you have people walking through different kinds of apartments. And then you can, for example, apply a simple model which cuts when you are in a different room. And then you can simply apply them to these reconstruction models like Pi3 and VGGT. And then you get these video-generated point clouds. They roughly look like this. So these are the best ones we could find. So they're not ideal, as you can see. There's a bunch of, for example, everywhere where there's white points, it means it didn't find any points, right? It doesn't mean there's a black hole in this room, right? It just couldn't reconstruct this. So it's not the best kind of data, but it is something, and you get it basically without any human labelers. And the important thing is these videos, no one will likely ever get 3D scans for them. Like A, we don't know where they are. B, like you would actually have to run through with an iPad, which has a LiDAR scanner or something like that, through these rooms. But instead, you can get by with slightly worse data, noisy data, but that you can scale infinitely much, which is extremely nice. And then, again, we have some sort of new laws, which I'm not going to go too much into detail here, which can deal a bit better with the noise we get from all of this. The key thing here is that we scale extremely well. So we have a few methodological contributions. Those are the first couple of improvements in terms of performance. But then I want you to focus sort of on this 1K to 16K data, which, okay, that gives us like 1.8% improvements. Okay, from 16K to 50K data, get huge improvements, and then we can make the model bigger as well once we have more data. And these are all improvements that you get for free. Like, we didn't collect any more data here, which is the whole point of this scalable pipeline. And so we can compare against other state-of-the-art methods. So state-of-the-art methods, as I said, they use, for example, number of real scans, I don't know, 20,000, did we say? So these would be the red numbers here that is sort of the previous state of the art. And then we can add one of our models, ends up here. We can add another one of our models, and we keep adding them. And since our video-generated point clouds, VGPC, we can just keep adding more and more. We actually get extremely nice performance gains without having to scale real data. So we're still at the point of using 0 real 3D scans for pre-training, but get really good performances. All right. And yeah, this method that we develop actually fits extremely well to this noisy data that we have, but it also works pretty well on clean data. So even if you did walk through a room with a LiDAR scanner, you can apply the same method and it performs pretty well. And the future is really moving to completely unsupervised geometry models. So these models that give you these point clouds, these sort of noisy but relatively good 3D scenes, they still rely on synthetic data and some supervision. There's some models coming out which can do without this, and it sort of works as well. So this is really the future, that we just put in videos and we get 3D models and 3D point encoders out in the end. And so here the summary is sort of that we have these video-generated point clouds as a real alternative, and we can, with this, really have scalable data pipelines that allows a huge new frontier for 3D learning. Or put differently, if you have 3D and SSL, you can just do both, and it works pretty well. All right, I think I want to have enough time for some questions. So the conclusion is videos are the new frontier, be it for 3D, be it for image understanding, be it for medical. So hopefully you take this away. Always happy to talk about collaborations, consultancy things. I know there's a bunch of companies here, so it's great, but also students, like always just email me, chat to me. I'm here, so thanks.
Thank you. Thanks a lot for this nice and insightful talk. So just a reminder, I will get to you first. We have questions in the room and remotely. I'll start here in the room. Just raise your hand. I will come with the microphone.
Hi, Yuki. Thank you. Great talk. My name is Matthias. I would like to ask you about a related domain, audio.
Mm-hmm.
Could you talk a little bit about how you can, or are there any ways to transfer your research findings into the domain of audio? I'm particularly interested in music and identifying musical melodies, things like this, chords, and so on.
Cool. Yeah, great question. Actually, that's a really nice thing about computer vision, is that, like, for a bunch of audio research, people just turn these into images. So they turn these into log-model spectrograms, which is like a 1D image, which you can make longer, and then they literally apply the same methods. So they also, for example, mask different parts of the image and let it reconstruct. They cluster different things. They apply some augmentations and try to have the representations be similar. In this case, the dense stuff might not make sense to say, like, this frequency band should be the same as here. But otherwise, literally, the methods which perform best on audio, the last time I checked, are the same, which more or less the same, which perform best on the image domain. And the same goes also that you do the pre-training on as much data as you can, and then a tiny bit of fine-tuning usually works really well. So at least for general audio. For speech, there's something else, but for general audio, and I've worked a bit with audio, that's just how we deal with it, yeah.
Thank you for the great talk. I wanted to ask, how much more efficient are your models as compared to other similarly performant models in training and also inference?
Right, it depends what we're comparing. So, for example, if we develop a new algorithm that trains models better, for example, using video data, we tend to use the same model, right? The same transformer with the same number of parameters. So once you deploy this, it costs the same for each forward pass. In terms of pre-training, you tend to need the same amount of compute. There's no way around that. I mean, you do. What we do, however, which is quite surprising, is this post-training literature. So we can basically take a model which has been trained on a lot of GPU hours, and then we just train it for 20 more GPU hours, like the type tuning work, and we get really big improvements. So that's just, that's pretty nice. So it's disproportionately, gives us a disproportionate positive effect, this post-training.
Thank you for the talk. I wondered, you were saying that instead of doing contrastive learning and then sort of having the language ingrained already in the model, you want to just train the video backbone or the image backbone. And then do you want to add speech later, or do you think like promptable models are just not something that are really as useful?
No, I mean, I think the key use case, at least for now, for vision models are multimodal LLMs. I mean, that's really extremely useful if I can send ChatGPT some image and it tells me what to do, right? But the key thing for me is like if we want to have image models that are extremely robust to noise, occlusions, all kinds of things, we want to train them just using images, because if you give them labels, they can always take a shortcut. They can, and I mean, you see this even in the clip-based models. For example, if somewhere it's written like you have something written, then it will just read it and not do the recognition of what's in the scene, for example. And that's extremely annoying if you're trying to learn robust image representations. Yeah. But yeah, I mean, combining it with language ultimately is the way to make them useful.
I hope that it still works.
Oh yeah, for sure. Yeah, and it does. I mean, people have combined self-supervised vision models in multimodal LLMs for a long time, and they actually complement clip-based models quite well. Yeah.
Thank you for the talk. I had a question about the self-supervised learning process. So as far as I understood, it was about dividing the images into patches for each of the frame, and then we compare the patches of the last frame to the first one. Like with the license plate example, I wasn't exactly clear how does the model learn that this license plate patch in this location is the same as the one on the top. Or
It makes sense that I also didn't explain how this was done. The basic thing is that we have a pre-trained model. This gives you a representation for every frame, and then you pick this patch, for example, where there's a license plate, and then you look for it where is the closest feature in the next frame. And you never find it exactly, but you get some sort of heat map. And then you take this heat map and you look for this in the next frame. And then you kind of have this heat map that flows through through the frames and ends up somewhere at the end. Yeah, that's how we do the tracking, basically. Yeah, thanks.
I was wondering, since you said you have some lack of data, if it makes sense to use simulated data from games or so, where you also have additional context. I mean, you know what is going on, you can place the objects where you want to have them and use that either for 3D or 2D training.
Yeah, so for the 3D paper, I mean, the best paper before ours used 140K scenes, and 120 of them were simulated, for example, right? So it does help. But this gap between simulated and real is still quite annoying. And it's still like you can keep getting better on simulated, but not getting any gains on real data. So therefore, in this paper, we opted for, okay, let's keep it real, basically, but use noisy data. So, but yeah, I mean, the more realistic the simulated data becomes, the more useful it will be. And once the model has learned some generic good representation of the real world, simulated data can be extremely useful for then, for example, training policies for robots, right? Because at that point, you really cannot collect more real data. That becomes really expensive. But the general perception of what objects are, where they are, things like that, real data is pretty good to go.
Thank you for the talk. I would have a question about the volume of the data and diminishing returns, especially for data that's very similar. I suspect you don't need 100,000 videos of Labradors playing on the grass, and maybe 10 will do. But if you are scraping YouTube, for example, you will probably get the first lots of duplicate data.
Yeah.
And you probably end up with too much data because you can't process it all. So what are strategies in that regard to deal with that?
Yeah, that's a great question. And that's also like actually one of the reasons why I'm trying to at least keep up with the LLM literature is that the LLM guys are a bit more advanced in this domain. So this domain of especially data curation matters hugely and is not being talked too much about in computer vision. But which data to pick at what point of the training is insanely important for all of these models. I mean, for LLMs, we know this. We have pre-training, we have mid-training, we have post-training. All of these have different data mixes. For computer vision, this isn't quite yet the case. I mean, We have maybe pre-training and post-training, but that's it. But this is becoming increasingly important, and we know very little about what data is good at what point. So if you want to do a postdoc, then
I think if you want to do a postdoc, his lab is actually going to be quite a good choice if you see where they're publishing. But are there more questions to our speaker? That was really nice. We ran over time, undoubtedly, huge room. So thanks again for your great talk and the questions.
all right, thanks.